Have you ever wondered how scientists can figure out exactly what's dissolved in a liquid even when it's in crazy small amounts? Well, we're going to dive into a really clever technique that uses electricity to create a unique chemical signature, an electrical fingerprint for substances you can't even see.
So, picture this. You've got a sample of water, right? And you absolutely need to know if it's got trace amounts of some metal or maybe a drug in it. The thing is, it's all completely invisible to the naked eye. So what's the first huge hurdle we have to get over?
That's the big question, isn't it? If you can't see it, how on earth can you identify it, let alone figure out how much of it is actually in there? Well, turns out you can ask it an electrical question, and the answer you get comes from a technique called polarography.
At its heart, polarography is actually brilliantly simple. You just apply a voltage to your solution, gradually turning it up, and you carefully measure the electrical current that flows through it. See, different substances react to that voltage in very specific, very predictable ways. But to get a really good, reliable answer, you need a very, very special kind of sensor.
And this, right here, is where the real genius of the technique comes into play. The entire process, the whole thing, it all hinges on one of the most unique electrodes ever designed, a tiny, perfect, and constantly renewing drop of liquid mercury.
So the single drop of mercury, that is the heart of the entire machine. It's our detector. It's where we ask the electrical question and where the chemical we're looking for gives us its answer. But how in the world do you create such a perfect repeating drop like that?
It's done with this really elegant setup. You have mercury from a reservoir that flows through the superfine glass tube, a capillary, and it forms a brand new drop every, say, 2 to 8 seconds. Each drop grows, does its measurement job, and then plop, it falls away, replaced by a fresh, perfectly clean one. So let's see how this one piece fits into the whole electrical circuit.
And here you see the whole shebang. The dropping mercury electrode, or DME for short, that's our active sensor. And to complete the circuit, it's paired up with a stable reference electrode. As we apply a voltage between them, we can measure the teeny tiny current that flows through each new drop of mercury as it forms.
So why? Why go to all this trouble with dropping mercury? This quote explains it perfectly. You see, with a lot of chemical sensors, the surface gets all gunked up or poisoned by the reaction, and that gives you bad readings. But the DME? It basically hits the refresh button every few seconds. This ensures that every single measurement is taken on a pristine, uncontaminated surface. It's self-cleaning.
Okay, so running the experiment itself follows these key steps. First, and this is important, we bubble nitrogen gas through the solution. Why? To get rid of any dissolved oxygen, because that little guy loves to interfere with our measurement. Then, we add something called the supporting electrolyte, which just helps the current flow nice and smoothly. Finally, we're ready. We slowly ramp up the voltage and record the current. All right, the experiment's done. What are we left with? Well, we get a graph, a plot of the current versus the voltage. And believe me, this isn't just any old graph. It is a unique signature, an electrical fingerprint for the exact substance we're hunting for.
And this is what the machine spits out. The result is a graph called a polarogram. This really distinctive S-shaped wave, that is the answer we've been looking for. The shape of this wave and its position tells us absolutely everything we need to know. So how do we read this fingerprint? It's all about two key features. The position of the wave along the bottom axis, that tells you what substance is in the solution. It's a unique identifier, like a name. And the height of the wave, that tells you the quantity. The higher the wave, the more stuff is in there. It's that simple. Position is identity, height is quantity.
Okay, so we can visually see what's there, and we can get a feel for how much. But how do we turn that wave height into a precise number, a real concentration? For that, we need to look at the elegant bit of math that actually governs this whole process.
This right here is the Ilkovitz equation. Now, don't worry, you don't have to memorize it. The really important thing to get here is that this equation is the direct mathematical link between the current we measured, that's the height of our wave, and the concentration of our substance. By plugging in our measurement and a few other knowns, we can calculate the exact concentration. It is literally the key to cracking the code.
So why does any of this matter? Well, the applications are all over the place. Polarography is used for everything from quality control in medicine, like making sure the right amount of an antibiotic is in a pill, to environmental monitoring for nasty heavy metals, and even for measuring dissolved oxygen in biological samples. It's a real workhorse.
Now, as brilliant as this technique is, it is not without its challenges.
And like any powerful tool, it's really important to understand both its incredible strengths and its undeniable drawbacks, especially when it comes to its key ingredient.
On the one hand, the advantages are clear. That constantly refreshed surface gives you incredibly consistent results, and it totally avoids the poisoning that messes up other electrodes. But the downsides are pretty serious. That tiny glass tube can get blocked, and most importantly, let's be real, mercury is highly toxic stuff. You have to handle it so carefully. It also has a limited range. You can't really use it at high positive voltages because the mercury itself starts to react.
But the story doesn't end there. The principles of polarography have evolved. For instance, a technique called amperoelectric titration uses the same basic setup but in a totally different way. Instead of just identifying something, it lets us watch a chemical reaction happen in real time. As we add a second chemical, the current changes, creating this V-shaped curve. And that sharp point at the bottom, that tells us the exact moment the reaction is finished.
Ultimately, polarography teaches us something really powerful. By applying a simple voltage and just listening carefully to the electrical response, we can uncover this whole hidden world of chemical information. It kind of leaves you wondering, doesn't it? What else is out there just waiting to be revealed if we can only figure out the right electrical question to ask?